Alright, so now we are going to do, instead of looking for when it's increasing and decreasing using the first derivative, we're going to do intervals of concavity. So we're going to find when is it happy and when is it sad. So second derivative, and then this has to do with happy or sad. Alright. So we want to find the x coordinates, so just the x values for all the inflection points. Inflection points are wherever it changes from happy to sad or sad to happy. And then we're going to find any discontinuities and find the open intervals where the function is concave up and concave down. So this discontinuity stuff is important, and I do want to talk about it. It's just basically whenever you have a hole or an asymptote. So whatever x is, it can't equal. But for regular functions like this, you won't have any discontinuities. Okay. The only ones you're really going to have discontinuities for are for like rational functions like number 4, because if x equals 3, then the function does not exist. Okay. So stuff like that. So any zeros in the denominator or negatives under a square root. Okay, so there's that. Okay, and we actually have the graph here for us, so we're going to be able to verify all of this stuff. So even just by looking at this graph, it looks to me like it's probably sad up until about right here, then it gets happy. Okay, so this is going to be a pretty simple one. So we're going to take the first derivative, (3x squared minus 6x). Then we're going to go ahead and take the second derivative, and that is 6x minus 6. Okay, so just like we used to do with our first derivative test for up and down, when is it increasing, when is it decreasing, we're going to set this equal to 0. And we'll find that if you add 6, divide by 6, x equals 1. So there's only one point that matters here. Okay, and that's going to be 1. And then all we got to do is, just like the first derivative, substitute in a value to the left and to the right to find the feelings. Okay, so I'll pick 0. So let's say I plug in 0 to my second derivative. 0 times 6 is 0, minus 6 is negative 6. So that's sad. And then to the right, we'll pick 2. So 6 times 2 is 12, minus 6 is positive 6. So it is sad and then happy. So at 1, we switch, so this is an inflection. Okay, and that's all we need. We basically can see that from this graph that that's true. It is sad, and then at x equals 1, it changes to happy. Okay, so we basically already had said that, right? But that's what we're doing. Again, for the ones you don't have the graph to verify, but you could always check in your calculator. Okay, but we're just looking for inflection points, and inflection points are where this changes. Okay, if it does not change, then it is not an inflection point. But pretty much any critical value you get, it's probably going to change. The interval part of concave up, concave down, we're just going to write that using interval notation. So concave up, that's the happy. So concave up is going to be from 1 to infinity. That's where it's happy. And then concave down is from negative infinity to 1. Okay, so that's all you got to do for these. Use the second derivative, find your critical values when the second derivative equals 0, and then plug in numbers to see where it's happy and sad and where there's inflection points. Okay, number 4 we'll probably go over together tomorrow just because it's a weird one since it's rational. And maybe the ones on the back we'll go over tomorrow, but I want you to go ahead and try those. You should be able to. Don't forget quotient rule, chain rule, chain rule, chain rule, Justin. Alright, cool. Y'all can try number 8. That sounds like fun. This is kind of what we did. We're giving y'all, where y'all are given values for the first derivative, for x, y points, for concavity, and you get to sketch it, kind of like what we did in class. So actually, that'll be a really good one for y'all to do. I'll see y'all tomorrow. Have fun testing, or not testing.